muted. I'll just share my PowerPoint. My sharing. Okay. Video. Hello everyone, good evening. We are going to wait for a minute maybe or two, then we'll start. If I'm audible, can you all please confirm or by writing it in the chat? Am I audible? Good evening, Vedant. Vedant, am I audible? Thank you so much, Vedant. And I hope so that you are able to see my screen as well. Yes, excellent. I'll request everyone to please write down your name, your phone numbers. I'm going to wait for a minute or two maybe, and then we will start. Good evening, Ansh. It's just about 4:02 right now. The official timing given for the meeting was 4. So I'm going to wait till 4:05. That's 3 more minutes, and then we will start. Pathan, walaikum assalam, Mohammed. I think we will start off with the session. Good evening, everyone, and welcome to Anis Defense Career Institute. My name is Sharjeel Sheikh. As we know, most of us know that we have been in this, we have been in the defense career services for the last 33 years, and we have more than 600 plus students who are serving as officers in, be it in Navy, Army, or Air Force. We're absolutely proud of it. Recently, one of the students got selected for Air Force. He had to give multiple attempts in order to get selected for the Air Force. It just goes to show that if you're really keen on serving the nation, even if you meet failure for the first time, you should still keep on going. There was an old saying when you were kids, try till you succeed. That really holds true for all the people who want to get into defense. Getting into defense is a very amazing thing. It's a very prestigious thing for everyone included, right? Because you're doing a very positive deed by doing so. We conduct these 4 p.m. lectures. A lot of times we talk about something which is related to the syllabus. A lot of times we talk about general awareness. For example, the next weekend, that is tomorrow and the day after tomorrow, we are going to talk about the new curriculum design that the government has given. I'm sure by now most of us would be aware that the government has launched a new, they have revamped the entire structure of how education is going to go, moving forward. We are going to talk about that on 2 days. I would request everyone to please attend that so that you're well informed and you could take decisions based on your understanding, because it's absolutely new. Whatever information we know, we would be sharing it with everyone. So I would definitely request everyone to attend those sessions, which would be tomorrow and day after tomorrow, the same time, 4 p.m. And today, I'm going to take a small topic called as mechanical waves. Understand the topic mechanical wave could be a bit misleading, as I'm not going to go into very depth of mechanical waves. What I'm going to do is a very basic concept, which is called as Crest and Trough and compression and rarefaction. Why did we choose such a basic topic for today, especially for people who are doing physics in 11th and 12th standards? Because we firmly believe that once your basics are sorted, everything else could be built on it. So today's topic, I hope so would be interesting for a lot of people, and I hope so that you enjoy today's session. On that note, let us begin with the session. See, generally, whenever we talk about waves, anyone, be it parents, be it students, be it anyone for that matter, the moment we talk about waves, the first thing that comes to our head is basically a sea wave. That's one of the first images that, gets into our head. That's one of the first images that we see whenever we talk about a wave. Precisely, it's a sea wave. Sea wave, is sea wave a type of wave? Yes, it's a type of wave, obviously. And is it a type of mechanical wave? Yes, it is, right? So are we going to only talk about sea waves today? No, we are not. Will we talk about some water waves? Yes, we will, right? Let me explain. A wave could be described as a disturbance that travels through a medium from one location to another. See, I'm not talking about exact definitions. This session is more for common people where we could understand these concepts from physics, right? Now, all I'm saying is, what is wave? If you want to describe wave, how do you describe wave? In the most simplest word, we could describe it as any sort of disturbance. Why am I using the word disturbance here? I'll be explaining that in about the next slide, all right? So a wave can be described as a disturbance that travels through a medium from one location to another. Understand, I've used a very specific term over here, that this wave needs medium. That means there can be any other wave that do not need any medium. I want you all to write it in the chat box and tell me which waves do not need medium and which waves need medium to travel, right? Because today we are going to talk about waves which need a medium to travel. So that is what we are going to discuss today. People, can you all write in the chat box and tell me which waves do not need a medium and which waves need a medium? Boys, come on. I'll give the answer in the end. All right, people are answering. Electromagnetic waves, as Sanket and Rudresh rightly said, electromagnetic waves do not need a medium. Sound waves do. When we talk about sound waves, we are basically talking about mechanical waves. Any and every mechanical wave will need a medium of propagation, right? I needed an assistant. That's why I introduced Tim. So everyone, let's say a hi to Tim. Tim is going to help us understand mechanical wave, or at least a part of it, right? Now, what does Tim say? Obviously, he says that he'll help us to understand waves. And he says, in order to do this, let's go to a pond. I'm sure all of you know what a pond is. It's a basically small water body, right? As Tim is walking towards the pond, that's a beautiful pond, people, right? Now, let's assume this. Let's assume this, what Tim does, or what any one of us would do, is you decide to, first and foremost, observe the surface of water. Can I say the surface of this water is absolutely calm and serene? Right? Yes. So students sitting next to me are saying, yes, excellent, thank you. Now, what if Tim decides that he needs to throw a stone in the pond, right? And let's assume that Tim is throwing. Let's observe. What happened? What do you think happened over here, guys? All right. Ripple Rudresh, you used the perfect word to describe it. What happened? What happened on the surface of water? It created ripples. But how was the ripple created? Because there was a disturbance. Excellent. Now understand why did I use the word disturbance with the uh, with I associated the word disturbance with waves. So what did the stone do to the water? You're going to understand this right now. Let's see. All right. Let's say we have a material medium, any material. I'm not going to specify it's solid, liquid, gaseous, or whatever. Let's say there's some material medium, which is this light pink color that you see over here. And let's say we know that every material is made up of some particles, right? So this material will also be made up of some particles. We name these particles. Let's say in this case, we name the particles as 1, 2, 3, and 4, right? Now, what do? We have a stick. Observe this carefully, guys, everyone, right? Let's say we have the stick, and what do we do to the stick? With the help of the stick, I disturb particle number 1 once. That's it. Remember, observe. I hit the particle number 1 once. Can I say particle number 1 will go and hit 2, 2 will hit 3, and 3 will hit 4. Now, I want to talk about this section for a moment. Everyone, how many times did 1 hit 2? Once. How many times did 2 hit 3? Once. How many times did 3 hit 4? Once. So can I say how many disturbance traveled across the medium? 1. How many disturbance traveled across the medium? 1. What is such a disturbance called as? A single disturbance going in the medium is called as what? Come on, Patafat write an answer. No, I'm not talking about a wave, Sanket. A single medium traveling along a medium is called as, all right. Anyone? Someone said, Vedant, not the exact answer. It's definitely a type of wave, but I'm saying a single disturbance. Okay, so I'll answer this. A single disturbance is basically called as a pulse. I'm sure you guys might have heard this word pulse a lot of times before. For example, whenever you're sick, we go to a doctor. Doctor will hold your hand over here, right, near your wrist, and it detects what? It detects pulse. What is that pulse? Your heart beats once, it sends out one single disturbance in the bloodstream, which the doctor can detect here, over here, and near your ankle as well, right? So what is a pulse? How do I define pulse, or how do I describe pulse? I could say that a single disturbance traveling through a medium is called as a pulse. I repeat, what is a pulse? It's a single disturbance traveling through a medium. I hope so that's clear, everyone. Remember, I was stressing continuously, that it is hitting only one time. So there's one single disturbance that was initiated by the stick, passed on to the fourth particle. So we say it's a single disturbance traveling through a medium. We are also going to try to see how does it work, but that comes later on. Before that, we need to dissect a wave, right? So that is basically what is a pulse. Now, what if I were to again take the same material medium? This is a material medium. I take again 4 particles in it. And what would be the names of these 4 particles? 1, 2, 3, and 4, right? Now, again, I take up a stick, but rather now, instead of disturbing particle number 1 once, what do? I keep on disturbing particle number 1 continuously. I take the stick and I just go ton on particle number 1. Okay? So observe what happens, everyone. Look at the animation here, right? The stick hits 1, 1 hits 2, 2 hits 3, 3 hits 4. But at the same time, 2 is also coming back, reversing and hitting 1, and 3 is also coming back and hitting 2. Do you see a pattern of disturbance over here? Do you see a pattern over here, guys? This pattern of disturbance is basically called as a wave. So remember, how did we describe the wave? Wave is basically a pattern of disturbance that can transfer, energy from one place to another. So when you disturbed the particles were also carrying energy with them. We'll try to understand what does that mean. Sorry. So in the most simplest word, if I want to describe a wave, I'll say it's basically speaking, it's a pattern of disturbance. What is it? It's a pattern of disturbance. So far, what have we learned? What do we know and what have we learned? We know that the pulse is a single disturbance. and a wave is a pattern of disturbance, two distinctive features that we know, right? So I'm sure if you you know, there's something called as pulsars in space. There's something called as pulsars, P-U-L-S, pulsar, not the bike pulsar, the astronomical object called as pulsar. Anyone knows about that? Quasars, pulsars. It's not exactly a star, but yeah, you could. It's a type of a star, not star, but yeah. Why is it called as a pulsar? Because it pulses. You know, it just pulses in equal frequency of time. In fact, fun fact to you guys: the first time when pulsars were discovered, I forgot the radio astronomers who first found these signals. So they found these signals, you know, coming at you at regular intervals of time, as precise as a clockwork. So they thought that they discovered alien civilization, and they found two pulsars. All right, they found two pulsars. At that time, they did not know it's their pulsars. They named it as LGM1 and LGM2. And when they announced the press briefing, they named it as LGM1 and LGM2. LGM1 basically stood for Little Green Men. So they actually thought that they had contact with alien civilization. Only later on, they realized that it is not that. It is an object which emits out X-ray and stuff, different sort of wavelengths. That was just a brief fun fact. I know it's not too fun for people who have not taken physics, right? All right, coming on to waves. Generally speaking, waves are of two types, as someone has already said in the beginning. First, electromagnetic waves, and the second would be mechanical waves, right? What is electromagnetic wave? As some people have already answered, some students have already answered in the chat box. It's basically a light wave. For example, a light wave is an example of a electromagnetic wave. And if you were to see the GIF over here, the speciality of an electromagnetic wave is it does not require material medium to propagate. Remember, I said mechanical waves need a material medium to propagate. Electromagnetic waves do not need a material medium to propagate. Why? If someone could research on that and tell me in the 9:30 lecture, that would be amazing. But for the others, I'd like to answer this here. An electromagnetic wave has two vectors, one being the electric vector, one being the magnetic vector. If you look at this closely, and if you could follow my cursor, you see on the y-axis, on the x-axis, on the y-axis, there's the electric vector, which is moving, the red line. And if you follow my cursor, the B written, B is basically the magnetic vector. So each helps create space for each other. That's how they propagate. Hence, they do not need any material medium. But the name of today's topic is mechanical waves. So are we going to discuss electromagnetic waves? No, obviously, right? So let's focus on mechanical waves, and mechanical waves are primarily classified into two types, which is transverse and longitudinal. I repeat again, transverse waves and longitudinal waves. We would be trying to understand them in some details today, right? So basically, classically, if you were to look at a transverse wave, this is the way in which a C wave, what you see, if you look at on the left-hand side with the heading transverse wave, that's how a transverse wave propagates. If you're to notice that the energy is going towards the right, but the particle is just going up and down. So if you're to look at the motion of the particle and the wave propagation, they are perpendicular to each other. In case of a transverse wave, we are going to talk about that in the next slide. For longitudinal wave, if you look at the particles is moving towards left and right, and the energy is also propagating in the same way. So we could say that both of them are parallel to each other. In longitudinal wave, the direction of propagation of a wave and the motion of the particle is parallel to each other. This image obviously doesn't do justice to what I'm about to say. So what we need to do is we need to go to the particle level and try to understand, right? So in order to do that, everyone, let's observe this. Okay. On the left, what we see, if you notice, it's a transverse wave. Classic example of a transverse wave. It looks like a C wave. On the right, what you see is a classic example of a longitudinal wave. Now, as I said, we need to focus on one single particle, what is happening to that. Then you will be in a better position to understand what I was saying. Let's have a look at the transverse wave. Okay, for both these waves, can we agree that the direction of propagation of wave is like this, horizontally? Can we agree to that, looking at the motion that is happening to these waves? Now let's only focus on one single particle, right? Let's look at this single particle. Just observe the single particle. It is just oscillating in a direction perpendicular to the direction of a wave. That means the particle doesn't have to change its place. It is just oscillating in the same space, right? So the direction of oscillation of a particle and the direction of the wave propagation is what? Perpendicular to each other. This is a fundamental characteristic of a transverse wave. Guys, I hope so you understood what I'm trying to tell you. Guys, did you understand what I was trying to say? Yes? No? No? All right. So observe, I'll just go back, wait. Look at this, the wave cut energy. If you look at this, it feels like the wave is going over here. Follow my cursor, people, follow my cursor. It's going like this. So this is the direction of the wave, this line which says. Now, if I were to talk about a single particle, look at this particle here. Is it going just up and down? So this motion up and down and this motion, can I say they are perpendicular to each other? That, my dear friends, my dear students, is the basic characteristic of a transverse wave. That the direction of the particle and the direction of the wave would be perpendicular to each other. Let's focus on the longitudinal wave. Over here, the direction of wave is like this, propagation of wave. Let's look at a single particle. See how this particle is moving. If you notice, it's just going left and right, right? So if you notice the direction of the wave and the motion of the particle, they're basically what? Parallel to each other. And this is a basic characteristic of a longitudinal wave. So one of the easiest ways to understand whether the given wave is transverse or longitudinal is to understand whether they are perpendicular or whether the direction of particle is parallel to it. Once you understand this, everything else will fall in place. No, I'll talk about that, right? All right, now let's try to understand this. As I said, these are the basic characteristics of transverse and longitudinal waves. Moving forward, let's focus on transverse waves right now, people, right? Have a look over here. If you look at the slinky, you understand a slinky? A slinky is like a spring. It's a toy that people play, a lot of children play. And look at the motion of the hand. So the particle is going up and down, and the wave, look at the wave, look at the swell. The swell is going in this direction. So the propagation is like this, the particle is like this. So we say both of them are what? Perpendicular to each other, right? Now, if I were to plot this, let's say if I want to, find the anatomy of a wave, and if I want to plot this, let's say we have the y-axis and we have the x-axis. Obviously, the y-axis has the displacement, whereas the x-axis has the direction of propagation of the energy. And if you were to plot it, this is what you get. You get the wave. This is also called as a sine wave. You get that function. Now let's try to dissect it and try to understand what are the different parts of a wave, right? The first thing that we need to understand, the peaks of these waves, are basically called as crest. I repeat, the peaks are called as crests, and the valleys are called as trough. So basically, if someone were to ask you, how does a transverse wave progress? It progresses in the form of crest and trough. It progresses in the form of what? Crest and trough. Obviously, the distance of crest above and the distance of trough below would be the same, right? Now, the distance between two crests, if you notice over here, the distance between two crests is equal to the distance between two trough, and that distance is called as the wavelength. And wavelength is represented by a Greek symbol called as lambda. I repeat, the distance between two crests, two consecutive crests, and the distance between two consecutive troughs is basically called as a wavelength, and that distance is represented by a unit called as by a symbol called as lambda. Correct? Similarly, the height of the wave, that is the distance from the top of the crest to the mean position, which is the x-axis, or the distance from the last point of the trough to the x-axis, that distance is called as amplitude. And amplitude, the symbol of amplitude is capital A. What does amplitude signify? Amplitude is basically, I'm sure you guys have heard the word amplifier. What does the amplifier do? A lot of people like to, put amplifiers in the car along with the speakers because it just increases the loudness of the speakers. So basically, when I talk about amplitude or amplifier, it just increases the loudness. So when someone says increase the volume and decrease the volume, what you're doing basically is increasing the amplitude and decreasing the amplitude, right? So this is the basic wave, and the distance from A to B, basically, that is one complete crest and one complete trough, is called as one single wave. That's one wave. Then from, let's say, if you were to follow my cursor from this point B till this ending point, that would be the second wave. Why is this important? Because we are again going to talk about that in some details, right? So let's try to again, that's the basic structure. Let's try to define things. As I said, wavelength, lambda is the distance between two consecutive crests or trough, and it is called as wavelength. What would be the unit of wavelength? Understand it is nothing but length because the name itself says wavelength. Vedant, no, amplifier does not increase the wavelength, right? So that would be meter. The unit of wavelength is basically meter. The second thing that we need to understand, the second property of a wave that we need to understand is something called as time period. What do you mean by time period? It is the time taken by a complete cycle of wave to pass a point. So this is a point, this is a point, and there's this wave, one wave, okay? The time taken by one wave to cross a point is called as the time period. I repeat, the time taken by a single wave to cross a point completely, that is the distance AB that is shown in the figure. So if I were to have this, observe this, if I could. Okay, let's say this is a point, red color laser, and the time taken by this wave to completely cross this point is called as the time period, right? Hold on, I'll switch off the laser, otherwise I'll not be able to. Amplitude, I think I've already spoken about the amplitude. It's basically the height of a wave, right? And it is to do with the increasing the loudness. Second thing, and a very important thing also that I need to understand, what would be the unit of amplitude? What would be the unit of amplitude, guys? Anyone, boys? What is the unit of amplitude? Meter. Thank you so much, Omkar, because at the end of the day, it is also height. And we know that the SI unit of length is nothing but meter. So when you talk about a wavelength, you talk about amplitude, it will always be meter. Coming on to frequency. The symbol of frequency is F. A lot of times they also use the Greek letter nu to express frequency. Frequency is the number of waves passing a point in unit time. I'll explain this, okay? Let's say you're standing on the beach. I know during COVID times, that is also a huge miracle to be able to go to a beach and stand there. And as you're standing on the beach, let's say there are 5 waves which come and touch your feet every second. Why are they touching your feet? I mean, God knows, right? So if 5 waves are coming and touching the feet every second, the frequency is 5. If there are 10 waves coming and touching your feet every second, what does it mean? The frequency is how much? 10. What if there are 100 waves coming every second? What does that mean? No, it basically means tsunami aaya bhag jao. No, but right. It's 100 hertz. The unit of frequency is hertz, H, capital H, small z. This is named after the Italian scientist named as Heinrich Hertz, right? So frequency ka unit is named after him. I hope so it's clear by now. 100 hertz. Thank you. Friedrich Hertz, right? Srivardhan, thank you so much. Tsunami and frequency. We get a formula. Also, we know that frequency is inversely proportional to the time period. Obviously, if you would have seen the definition of frequency and time period, they are inversely proportional. So we derive a formula which is frequency is equal to 1 upon time. And when we know this, we also know the formula for speed, guys. We studied this in your 6th standard. Speed is equal to what? Distance upon time. So if I were to modify this to suit this wave, I could write Sorry, just a minute. No. So I could write what? Velocity is equals to what? Distance. Distance would means what? Wavelength, that is lambda, into time period. But 1 upon t is frequency, so you get a formula v, that is velocity, is equals to frequency into wavelength. That's one more formula that you could keep in mind. Now that we are talking about a wavelength, let's also talk. I'll show you how does a wave what happens in a wave. So for this thing, let's say we have a tap. We have some water in the bottom, the blue section. On the right hand side, you could see that we could control the frequency and the amplitude. Right now, I'm not doing anything. I'm just switching on the tap. As one drop of water falls, observe what happens. Right? It disturbed the particle. So that drop is just continuously disturbing the particle at that point. It is creating transverse wave. I hope so you could see that. Now, what we could do is, I could change the amplitude. See, if I were to change the amplitude, the height will also change. Now I'm reducing it, small amplitude. If I make it 0, nothing, because the wave 0 amplitude, what does it mean? There's no wave. There's nothing which is happening. And if I were to increase, and let's see the maximum amplitude. So basically amplitude basically means what? Height. I hope so this representation makes it absolutely easy for you to understand. At the same time, as I was explaining you guys about frequency, I can change the frequency. If I make it minimum, see what happens. 1, it's all the sweet time in the world to have only one disturbance. And as we grow slowly and steadily increase the frequency, see, we see a change in the wave. If I were to keep it maximum, this is what happens, right? I could slow it down if you all want, for you all to see. Or we can also plot a graph. This would be the graph. I can just reduce the frequency by something and also change the amplitude. If you look at the graph, it is exactly corresponding. The dotted line indicates basically the x-axis, right? And obviously, water level is marked on the left-hand side. If you look at the graph, this is the water level, x-axis, and you see your crest and trough. If I were to increase my amplitude, you will see that the water goes down further below, right? I hope so this makes easier for you all to understand. So the amplitude changes with change in frequency. No, I changed the amplitude. Frequency and amplitude are independent. Okay, you want to see the top? I don't think so. Top view, you'll be able to understand anything in top view. It just show you the differential pattern. Side view is better for you all to understand right now. We will be using the top view for something else right now today in today's class itself. Guys, I hope so. Is that clear, everyone? Isn't this like a cool bit of simulation? You see at what water level a tsunami occurs. At what water level? No, tsunami, for tsunami, what is necessary is not a water level. What is important is where the source of the earthquake was. And then even if it's deep, let's say the water is deep in that area, 50 meter, 100 meter, the surface would not be impacted. But then if the closer it comes to the shore, the amplitude of the wave increases in that case. So this swimming pool, this phenomenon occurs. It can happen everywhere, my friend. Wherever there's water, if you have a swimming pool, put in a tap and you could. But the only thing is, in this, it's clearly observable and you can control the amplitude and everything else, right? On that wonderful note, you're going. It could happen in your bucket while you take a shower. And that could happen wherever water is available, right? It rained a lot about a couple of minutes ago. No, it happens. Sound waves. Water is easily visible. You cannot see sound, so that makes it a bit challenging, right? Let's talk about longitudinal wave now. Same thing. If you look at the motion of the hand, it's going to and fro. And if you look at the compression, it's also traveling in the same direction. So you see there's some rings which are closer to each other. That is called as compression. And you'll see that there are some rings which are stretched away. That's called as a rarefaction. So longitudinal waves travels in the form of compressions and rarefactions. right? Understand. So, okay, this is a classic, comparison between how a transverse wave travel and a longitudinal wave travel. If you see a transverse wave, it goes like, this crest, and longitudinal is going in the way of compression. So for longitudinal wave, what is compression could be considered as the crest for transverse, and what is considered as rarefaction for longitudinal can be considered as the trough for transverse, right? So they could be extrapolated in better understanding, right? So we are going to talk about this. Is one more example, a classic example, using a tuning fork. If you know about something, the anatomy of a tuning fork, this handle basically is called as a stem. This one single-sided thing is called as a prong, P-R-O-N-G. So one prong, one more prong. Together it is called as what? Two prongs. No, it is just called as prongs. And if you look right next to it, what it shows is there's air. Air is invisible. Before it starts, you'll notice that, it's equidistant. The moment the prong moves out, it compresses the air. And then when it starts coming in again, due to the elasticity of the air, it will again extend it and expand it, hence creating a rarefaction. I'm sure most of us would have studied this in your 9th standard or your 10th standard, right? Again, remember I was talking about compressions, and these are the rarefactions. Again, compressions could be extrapolated to crest, and rarefaction could be extrapolated to, see, this is the example. So the compression could be associated with the crest, and the rarefaction is associated with the trough. I wanted you to understand so that you understand the wavelength wala funda very easily. See, so the wavelength is basically what distance between two compressions or the distance between two rarefactions, right? It becomes really easy for us to understand this. Can we say transverse wave travels faster than longitudinal wave? Not necessary. Not necessary. Academic extrapolation, important concept in maths too. Yes, definitely. Right. So, see, if you have understood this, all the other quantities, the wavelength, the you talk about the amplitude, you talk about anything else, they all stay the same. That time period, the frequency, they all stay the same. So only I just wanted to highlight how you could take the longitudinal wave and superimpose it on the transverse wave. Superimpose. I just remembered what is superposition quantum physics. Anyone knows about that? Superposition. It's a pretty interesting concept. If anyone knows, that would be amazing. All right, moving forward. So we need to do the same thing for sound. Before that, I'm just checking one thing. Wait. Only heard Vedant. Okay, Vedant. We can discuss that in someday in the 9:30 lecture. All right. So guys, so again, we need to do the similar thing. We have a speaker right now. I'll switch it on, and we could see the waves. Yahan pe top view, side view really doesn't make any difference because sound travels in all the directions, right? And if you notice, right, if I change the frequency, again the same thing. You see how as the speaker is moving, it is inducing. So look at the movement of the speaker and how the wave is propagating. So that's longitudinal wave basically. And as I were to change the frequency, see the vibrations increase. I could reduce it. I could reduce the amplitude. I could completely make it 0, but then when I make it 0, then there's no point in wave because, okay, why? If I were to make the amplitude 0, the sound waves stop. Why? There's no sound, so you cannot hear anything. So hence there's no sound, right? Also, those of you who have put in headphones, mind you, I'm going to play a tone. This is high. This could be a high pitched tone or low pitched tone. We are going to control that, and you will see how when the frequency changes or when the amplitude changes, how does the tone change? So fair warning to people with headphones, right? Listen to this. Are you able to hear? Okay, there's no. You're not able to hear it, right? Because even I'm not able to hear it. I don't know why. Ideally, Okay, I'll just check what's happening, because otherwise it does place the tone. Wait, I'll switch it off. I'll switch it off first. See, as I switch off the speaker, you see the sound travels and ends finally. I would see if I could. When I was experimenting, it was playing the sound. I don't know what happened, guys. If you all bear with me for a moment, I could reload this entire thing if you want. Oh, that's a resetting. No, sorry. My apologies. I couldn't. I wanted this to be, heard and seen, so you would clearly understand the difference between how, if I were to change the frequency, how the sound changes, and how it happens. But you guys can't. That's okay. That's why the ceiling of conference also always made curved. Yes, that's what you're talking about, Srivardhan, is about reverberation. Right, I'll talk about reverberation if you're interested in that. Guys, anyone can hear? No, I cannot. This, by the way, is how particles of air would behave if I were to change the frequency and the amplitude. I don't know. I'm not able to play the tone for some reason. I'm really saddened by that, because that was my, the piece de resistance. That is what I wanted it to be. Anyway, it doesn't matter. Not everything what you want in life that you'll get it, right? Anyway, so these particles, what you're seeing are air particle, and observe them as I were to change the amplitude. So this is what happens in your room. When you switch on your stereos, when you switch on your music system, the air behaves in this way. And as you go on increasing the volume, see what happens. What if I were to decrease and then increase the frequency? Let's say if I were to increase the frequency. Not a lot is happening, right? It's going very slowly and steadily. See, frequency is minimum. All right, I'll increase this and I'll increase this. Observe what happens to the air. You see, there are legit gaps in between. It's going so fast. This is precisely what happened when you put in earphones in your head. This is what happens. I did increase the amplitude as well. I did share the computer sound. If you want, I could try to do that again. I did share computer sound. Who was that? Rishikesh. Yes, I did that, but it's not. All right. All right. I think enough of this. If you want to see the side view for this, it won't make a difference. I could show you a pulse. Wait, I'll just show you. This was selected, right? I'll show you a pulse. Look at this, huh? We discussed a pulse, right? See what happens. Single pulse. You see that single thing is traveling? You'll be able to see it better if I were to do this. Okay, look at the pulse. We could also do that in the water thingy. Pulse, as I said, is a single disturbance in the material medium. Let's try to go back and see if we could do this with the water. Sorry. All right, so we have the pulse here. We'll wait and we'll see what happens. See? Right, did you see that, guys? Pulse? Just a single pulse. Right, someone was talking about reverberation, right? We could definitely discuss reverberation. What is reverberation, guys? Anyone can tell me what is reverberation? Any one of you who can tell me what is reverberation? These just represent air. By the way, fun fact, a duck's quack does not echo. Not necessarily reverberation does not happen only in an auditorium. It could also happen in your bathrooms. A lot of times when you're in a washroom, and a lot of people are bathroom singers, they like to sing while taking a shower or whatever, right? So you might often heard that when you try to sing, you have this reverberating effect, right? Someone said, Sahil, exactly, it's a prolongation of sound. And what happens when you're hearing that extension of sound, that small extension of sound, basically what you hear is called as reverberation. In fact, a lot of times this reverberation is undesirable, right? Because it is undesirable, so when auditoriums are being constructed, when theaters are being constructed, a lot of people have to, call in sound engineers and sound designers, which would tell us how to do and what to do, have sound absorbers. We use wallpapers, excellent, but it has to be a different grade of wallpapers. You could use different sort of ceilings. We could have these hollowed out wooden boards, in the room. All of them act like sound absorbers. So if you're getting, and if you're into a studio and if you're doing something like that, you will need to be able to create a perfect environment so that there's no sound absorbing that is happening. That is what is happening. If there are parents over here sitting in this session, I would like to give you one more fun fact about reverberation. There's this very old movie. I'm not sure parents would know. I'm not sure about the students. This movie is called as Mughal-e-Azam. Pretty old movie, yeah. There was this famous song. By the way, the music director of this movie was someone called as Naushad. The director was K. Asif. So in one particular scene, the protagonist, the so-called Anarkali, was standing underneath this huge dome, right? And she was singing. The director wanted the reverberation effect to happen in those days, in that particular stanza. That song was sung by none other than the legendary Lata Mangeshkar. In those days, we did not have any artificial machine to induce reverberation. Today, a basic laptop could induce reverberation, could have different sort of sounds, but not in those days. So that stanza was recorded in the washroom. The music director made Lata Mangeshkar stand in the washroom and record that one single stanza. And the reverberations were recorded in the tape. Hence, even today, we are able to hear those reverberations. Someone said, what is, sir, echo, desired sound and reverberation? No, even we don't desire echo, we do not desire reverberation. Echo is only desirable when you're standing at an echo point. That's the only time when people, they just yell at the top of their lungs just to be able to hear their own voice back again. They could have simply recorded and hear it again, but I don't know what's the fascination with the echo point. What is the minimum distance for an echo to be heard, boys? What's the minimum distance for an echo to be heard? 3 meter. No, Gaurav, that is not right. 17 meter, 8 meter. Nope. Minimum distance would be 17 meter between the observer and the reflecting surface. It could also be 17.2 depending on the velocity of sound. See, the velocity of sound keeps on changing. The velocity of sound can change because of temperature, because of humidity, because of atmospheric pressure, and a lot of things. So the generally accepted value of sound that we consider would be 340, 334 meters per second, right? And hence, an approximate distance that has to be maintained for an echo is 17 meter. In some places, it has to be more than 17 meter. Can it be less than 17? What happens on the peak of mountain for echo? Rishikesh, I did not understand your question. What happens on the peak of mountain? As in, you understand, I am sure most of you have gone to a hill station. A lot of you must have been to a hill station. And if you have been to a hill station, understand you cannot go anywhere and shout. You cannot simply go to any goddamn point. You cannot go to the sunrise point and say something, and it would the echo would happen. No, it wouldn't. So what is so special about the echo point? Is it that echo point के सामने जो पहाड़ है वहाँ पे एक बंदा छुप के बैठा है, and the moment you say something, and if you say Rishikesh, the सामने वाला बंदा will say Rishikesh, Rishikesh? No. Observe this next time you go to a hill station, everyone. Always the mountain opposite to the echo point will always be very stony and rigid. Whereas everywhere else, the mountain would usually be, covered with a lot of vegetation, a lot of greenery, a lot of loose mud, because these vegetation, trees, loose mud, they act like sound absorbers, because of which, whenever you say something, that sound gets absorbed and there's no echo that happens, right? Inside a cave, it will definitely happen because cave have multiple reflection. Also, reverberation also happens because of multiple reflection by a phenomena called as multiple reflection, right? I'm sure you all know what is a reflection. The word reflection simply means bouncing back. When I talk about multiple reflection, it is getting bounced back multiple times. It is as simple as that, right? Bounce back. Thank you, Shri Vardhan. Right. That is it from my side. I think anyone else from Anis, if you're online, would you like to say something before I end the session? By the way, people, we all know that tomorrow and day after tomorrow, we have this session for the change in the entire system of education, the educational revamping that is about to happen. So please do attend that session. It's at 4 p.m., 4 to 5, same like usual, tomorrow and day after tomorrow. That is over the weekend. Everyone, I'll request you to be there, please. And also, what time? 4 p.m. That would be at 4 p.m., 4 to 5 p.m. Right. For if there are physics teachers in the session today, you know, these simulations I've just used to, it's just the same simulation. Actually, I could change it from here. It's for water, sound, or it could also happen for light. And we could, you know, switch it on and we could see how light is, it's what's happening. FIT, the name is PHET, FIT simulations. It's been for more than 10 years. Colorado University is doing this. So if you happen to need it, it's for, you know, the kinetic energy changes. It's for all of those things. So if physics teachers could use it, that would be wonderful. You could easily incorporate them in your presentations, provided that your system is connected to internet connection, right? So I think that's all from my side, people. I hope so it was helpful to people. Fezansa, I'll request you to please copy the chat and save the chat and the participant list. What is the name of this? Ashish, what do you mean by this? The simulation? Colorado University has this simulations. They're called as simulations. They used to be in, I think, HTML. Now it's in Java. I think it's not an application. It's available on the website. It's free of cost for all teachers and students. I will encourage the students to please go ahead and play with these. Literally play with these. There's for electronic circuits. There's for magnetism. There's for a lot of things. No, you do not need any code. You do not need any code for this. FATE, right? FATE simulation. If you to Google FATE simulation, PHET, you'll come to it, right? For Desmos is for mathematics. This, what I know, is for physics, right? All right, people. Thank you so much, everyone. Have a pleasant weekend. Enjoy. Take care. Thank you all. If anyone, Fezansa, if Anisa is here, if anyone wants to talk, that should be okay. Otherwise, we could end the session. Fezansa, are you there? Jai Hind, Sri Vardhan. Jai Hind, everyone. Fezansa. Walaikum Assalam, Oman. Jai Hind, everyone. All right, I don't think so anyone is here. I'll just go ahead and end the session right away. Right, people, wonderful being with you all. Thank you, everyone. See you later. Bye-bye.